Math 2414, trigonometric integrals, miscellaneous trig integrals. I'm going to go ahead and put part 1. I might do a part 2, I might not. Because as I mentioned in the previous video, it's impossible to categorize all the variations of trig integrals because there's always going to be something missing from that list. So, let's just jump in and see what happens. Sorry, kind of hungry. Let's integrate cosine to the 5th power of theta times sine to the 4th power of theta d theta, which does not fit nicely in under our two previous categorizations of products of sines and cosines and products of tangents and secants. By the way, there's a third categorization for cosecants and cotangents, but I don't want to overload you with memorize all this. I want you to understand approaches and what to look for. So let's take a look at this one. There's a strategy for integrating trig functions that says if you have no clue how to start, make everything sines and cosines, and then reanalyze. So we're going to try that. We're going to try writing everything in terms of sines and cosines using some identities. For example, we have a quotient identity that says cotangent of theta is cosine theta over sine theta. So cotangent to the 5th power of theta is cosine to the 5th power of theta over sine to the 5th power of theta times sine to the 4th power of theta d theta. Okay? Well, we can cancel some of the signs. 4 of these cancel 4 of those. So this is equal to the integral of cosine to the 5th power over sine. So cosine of the 5th power of theta over sine of theta d theta. All right, well, the good news is we have it in terms of sines and cosines. The bad news is one of them is in a denominator, which makes us wonder, can we use our sine-cosine strategy? Our sine-cosine strategy is to pick on an odd power. Our sine-cosine strategy says if you have an odd power, let u be the other trig function. Well, in this case, we have 2 odd powers, but one of them's in a denominator. So I don't know if this sine is easily usable as part of the du package because it's in the denominator. So I'm kind of thinking about this in terms of building the du package. If I'm going to borrow something to stick over here for the du, I would need to borrow it from the top. It's not impossible to borrow it from the bottom. The way you would borrow a sine is you would throw a sine here and then bump the power up by 1. And then we could say let u equal cosine and go from there. But I'd like to use what's there and not bring in unnecessary stuff or extra stuff, if you will, if I can avoid it. So in my mind, what I'm thinking is I'm going to prepare this for a du package that has cosine theta d theta because I have got 5 cosines on top and I'm going to borrow one of them. So if I kind of reverse engineer this and think of this as the du, then what would u equal? Whose derivative is cosine? Sine. So let's let u equal sine theta, du equal cosine theta d theta, to work around this du package. Now we want sines and we have one, so this guy's going to become a u. But our unwanted trig function is the cosine, but it's in even power, so we must be on the right track. Recall that we can write cosine to the 4th power as cosine squared squared. And the reason that's advantageous is because we have a Pythagorean identity that says that we can replace cosine squared theta with 1 minus sine squared theta. So this becomes 1 minus sine squared theta squared. And now we can replace that sign with the u, which means our integral is now u on the bottom, du out to the side, 1 minus u squared squared. Now we're not out of the woods, we still got to figure out what to do with this, but this is fairly standard from an algebraic perspective in the context of integration. We don't integrate products, so we can multiply the top out, but we don't really integrate quotients either, aka fractions, so we can split this into 3 fractions and take it from there. So our strategy is to write this out twice and multiply it, split it into 3 fractions, and then take it from there. I'm going to move this upwards. So we have the integral of, let's go ahead and figure out what 1 minus u squared squared is. 1 minus u squared times itself, If I multiply it out and put it from highest to lowest power is u to the fourth minus 2u squared plus 1. This is all over u. And now it's actually reverted to a calculus 1 integral, and the strategy here is to split this into 3 fractions and reduce them all. U to the fourth over u is u to the third, minus 2u squared over u is u, plus 1 over u. These are all easily integrable. And remember that u is equal to sine of theta. The integral of u to the third is 1/4 u to the fourth, so undo the substitution to get 1/4 sine to the fourth theta, minus the integral of 2u is u squared, so it's going to be sine squared theta, plus the integral of 1 over u is the natural log of the absolute value of u, so the natural log of the absolute value of sine theta, plus c. So that one actually turned into a sine-cosine situation. It just didn't start that way, and it was a slightly different situation because our sines and cosines were involved in a quotient, aka a fraction instead of a product, but it still got the job done. All right, let's try this one. Integral of cosecant to the fourth, cotangent to the sixth. I must admit that I left out a third categorization of trig integrals. There was the one involving powers of sine and cosine, and the reason those were together is because of the Pythagorean identity connecting the two. There was one involving the product of secants and tangents, which were together because, oh, I forgot, on sines and cosines, their derivatives are related and they're connected in the Pythagorean identity. For secants and tangents, their derivatives are related and they're connected in the Pythagorean identity. But a third categorization is a product of cosecants and cotangents because their derivatives are related and there's a Pythagorean identity tying them together. So instead of writing down this, that, and that, let's just jump in and try something. But I do want to remind you about the derivatives of cosecant and cotangent. The derivative of cosecant is just like the derivative of secant, which is secant tangent, except it's negative in all the cofunctions. Negative cosecant x, cotangent of x. And the derivative of cotangent is like the derivative of tangent, which is secant squared, except it's negative and it's cofunction. So instead of secant squared, it's negative cosecant squared x. And if these derivatives are slipping your mind, go back and watch the Calculus 1 review videos over derivative rules. All right, so we have a mess of secants, cosecants and cotangents, so we have one of two choices. Let's let u equal cosecant, let's let u equal cotangent. And we can review the even and odd power things, but let's just pretend that we don't know those for a second. Let's just pick one. Let's pick u equal cosecant of x. This may or may not work, I'll be honest. Hadn't thought about it much. Then du is going to be the derivative of cosecant is negative cosecant x, cotangent x, dx. And let's think about our general strategy. We borrow to make the du package, and the unwanted trig function should end up with an even power to take advantage of the Pythagorean identity. Well, if we borrow a cosecant and a cotangent, both of these drop down to being odd powers. Our wanted trig function is cosecant, our unwanted trig function is cotangent, but borrowing one of it would reduce it to a fifth power. That's not even. This must not be the right choice. So let's not use cosecant. So let's use cotangent. And again, if you committed to memory the rules for integrating products of secants and tangents, it's really the same rules for cosecants and cotangents. But I would rather understand than just memorize. We tried cosecant, it didn't work. Let's try cotangent. If we said u is cotangent of x, then du would be negative cosecant squared of x dx. So let's think this out. We would need to borrow two cosecants for the du package, so this would knock down to cosecant squared. Our wanted trig functions are cotangents. Our unwanted would be the cosecants. It would be an even power cosecant. We're on the right path. All right, so let's prep this. Let's pull off two of the cosecants for the du package. So that'll be cosecant squared. Leave the cotangents alone. Put the cosecant squared over here with the dx, but our du package also needs a negative, so balance out some negatives, and let's take inventory. All this is our du package. Our wanted trig function is cotangent, and we have 6 of them, so that's u to the 6th. But we don't want the cosecant, and it has an even power. Cosecant squared is equal to 1 plus cotangent squared, or cotangent squared plus 1. This is why knowing your trig identities is kind of critical. Cotangent is the trig function we want, so cotangent squared x plus 1 will become u squared plus 1. And now everything is ready to integrate. We have negative integral. Let's go ahead and distribute this to get u to the 8th plus u to the 6th du. Let's integrate, distribute the negative, and unsubstitute. It's not as bad as it sounds. Everything's going to end up negative. The integral of u to the 8th is 1/9 u to the 9th. Don't forget the negative. But u is cotangent, so negative 1/9 cotangent to the 9th x minus the integral of u to the 6th is 1/7 u to the 7th, but u is cotangent, so 1/7 cotangent to the 7th x plus c, and it's over. I can't stress enough that understanding the flow is way more important than memorizing a bunch of rules, at least from a theoretical mathematician's perspective. If you're applied, memorize away, but trust me, the more you understand, the less you have to memorize. All right, let me check the time on this. I was tempted to do one more integral. You know what? I am going to do one more so that we don't have a part 2. It's going to be a quick one. And in case you want to go ahead and write it down, it's the integral of 1 over cosine x minus 1. The minus 1 is in the denominator. 1 over cosine x minus 1. Let's go ahead and write it. I really wanted to do this one because it shows a technique that's based in both algebra and trigonometry. The problem here is if you try to just do a direct technique like let u equal the denominator, you have nothing to create the du package. If u is equal to the denominator, the derivative would be negative sine x dx. There's no signs inside. And although you could artificially create one, it's gonna by putting a sign on top and a sign on the bottom, it's gonna create more issues. There's a trick here. This is a trick that was not taught to me. It was a trick that was eventually figured out, and I was like, why isn't this just taught? If you have 1 plus or minus cosine or sine or vice versa. In other words, if you got an addition or subtraction problem involving a sine or a cosine and the number 1, you can create a Pythagorean identity out of thin air. The trick is recognizing that when you multiply a difference times the sum, you get a difference of squares. And every Pythagorean identity can be rearranged to be a difference of squares. For example, we can change, if we had cosine squared x plus sine squared x is equal to 1, we can move this sine squared over and say cosine squared x is equal to 1 minus sine squared x, which is a difference of squares and hence would factor. So what's the strategy here? If you have half of a factor pair, it would be nice to have the other half. If you have a difference, it would be nice to multiply by its sum to create a difference of squares. And in this case, create a difference of squares that's embedded in a Pythagorean identity. So the trick to this, and I hate calling it a trick, but it's just knowing where to look and go, aha, you are half of a product that equals a difference of squares, which might turn into a Pythagorean identity. So the trick is to multiply both sides of this fraction by cosine x plus 1 over itself. You can always multiply a fraction by 1 to preserve its value, as long as that fraction is defined. So we are assuming that cosine of x is not equal to negative 1. But if I multiply both sides, it will give me cosine of x plus 1 on the top. On the bottom, if I multiply that out, I'll get cosine squared x minus 1. And now is where you have to be very good with your Pythagorean identities. If I go back to this one, and I wanted to make cosine squared x minus 1, the cosine is already positive. The cosine squared is already positive, so I need to leave it there. If I move the 1 over and move the sine squared over, I'll get cosine squared x minus 1 equals negative sine squared x. So let's see what that does. I'm going to put the negative in front, don't forget it, sine squared x. All right. Well, now what? Well, another strategy is to split a fraction into 2 fractions and clean it up. So cosine x over sine squared x. I think I know what I'm going to do there. I know exactly what I'm going to do there. Plus 1 over sine squared x. Let's move all the sine squareds up. I got two ways to move something up when it's a trig function. Number one is to make its power negative. So we could say sine to the negative 2x cosine x. Number two is to use its reciprocal function. The reciprocal of sine is cosecant, so the reciprocal of sine squared is cosecant squared. And for full disclosure, I did not work out this problem in advance. I am figuring it out as we go along. But I do see the path to the end, so I know we're okay. This integral I'm not worried about because the derivative of cotangent is negative cosecant squared, so I can bring the negative in. That antiderivative is, in fact, let's go ahead and split this. Integral of negative sine negative 2x cosine x dx plus the integral of negative cosecant squared x dx. This is just the derivative of cotangent, so I'm okay there. I'm done with that part, so yay. But how are we going to integrate sine negative 2x? Negative sine to the negative 2 power of x cosine x dx. Let's move that over here. Negative sine to the negative 2x cosine x dx. And the answer is, with a little bitty substitution, if we let u equal sine of x, then du is equal to cosine of x dx. This is standard sine-cosine product integration technique. All this becomes du, so this is the integral of negative u to the negative 2 du. Just integrate it by adding 1 to the power to get negative 1, dividing by the new power, and we still had a negative in front. And so the negatives cancel, and this becomes 1 over u, but u was sine, so this becomes 1 over sine, which is cosecant. So our answer is cosecant plus cotangent. Therefore, the integral of 1 over cosine of x minus 1 dx is equal to that answer, cosecant of x, plus this answer, cotangent of x, and of course, plus our constant of integration. I'm smiling because I literally did, I knew the first move, I knew to multiply by the conjugate. A conjugate of an addition problem is just the corresponding subtraction problems and vice versa. Anyway, I knew the first trick about multiplying up here. I really didn't know how the rest was going to play out, so I'm kind of happy that I could see the path towards the end. All right, I think that's enough for this series.